All right, so you know how sometimes you've got all these numbers, right? And you're kind of wondering, is there actually a connection between these things? Well, today we're diving into that with regression. It's all about seeing if one thing really does influence another, at least in your data.
Yeah, exactly. You actually sent over these YouTube transcripts from this Savoir-faire digital channel, and they're really hands-on with simple linear regression. They use R and RStudio too, which is cool.
Yeah, definitely. So today we're trying to give you a clear and practical understanding of linear regression. We'll start basic, but we want to get to how you can really tell if this is a good way to analyze your data. We're not going to get bogged down with tons of math, though. Don't worry about that. And we're sticking with the simple linear regression stuff here, so it's all about the relationship between two main things.
Right, just two. Like we're drawing a line to show how one variable changes when the other one does. That's the basic idea.
Okay, so then let's just jump right in. What even is simple linear regression? Like if you had to explain it simply.
Well, it's modeling how one thing, this dependent variable, which we call y, and that's what you're trying to predict, is affected by another thing. That other thing is the independent variable, or x. We're assuming here that the relationship between them is a straight line.
Okay, straight line. So then there's that equation, right?
Yeah.
It's a y equals b0 plus b1x plus a. I know it looks a little scary, but
Oh, yeah, we can break it down, don't we? That B0, that's the intercept. Like if you picture a graph, it's where the line crosses the vertical axis, the y-axis. It's the value of y when x is 0.
Gotcha. Okay. So if we were plotting something like how tall a plant grows, that's our y, against how many hours of sunlight it gets, so that would be x, then the intercept would be like, what? The plant's height with no sunlight.
Theoretically, yeah.
Yeah.
Which might not make a ton of sense in real life. Like a seed probably needs at least some sun to sprout. But in the math, that's what the intercept is on our line.
It's a starting point.
Yeah, exactly. And then you've got B1. That's the slope. This is the really key part, I think. It tells you how much y changes for every 1 unit increase in x. So how steep the line is.
So is it always going up?
No, not necessarily. If it's a positive slope, that means as x goes up, y goes up too, like more advertising spending, probably more sales, right? But a negative slope, that's when x going up means y tends to go down. Like maybe something gets more expensive, fewer people buy it.
Okay, that makes sense. And then we can't forget that little a at the end, the error term.
Right. They're just acknowledging that our straight line isn't going to be perfect. Real data is messy. There's always stuff we're not capturing in a simple model.
So it's like the difference between what our model predicts and what we actually see happening.
Exactly. And it's all that variation and the fact that a straight line is just an approximation.
Okay, so we've got the equation down. But how do we find the best values for B0 and B1 from all this data?
Right. So the goal is to find the values for B0 and B1 that give us the best fitting line for our data. And the usual way to do this is something called ordinary least squares.
Ordinary least squares, or OLS.
Right, OLS.
Okay. That sounds kind of complicated. Can we break it down? Like, what's the basic idea there?
Sure. Imagine you've got your data points all plotted on a graph.
Right.
Right? And you're trying to draw a straight line through them. Some points will be above the line, some below. OLS basically finds the line where the total distance of all those points to the line is as small as possible.
So you add up the distances?
Well, not quite. You actually square the distances first and then add them up. That points that are way off the line have a bigger impact on where the line ends up.
I see, I see. So you're saying if a point is really far away from the line, it gets kind of penalized more, right? Helps make the line fit better overall.
Exactly. And, the transcripts you shared get into the practical side of this with R and RStudio. They use this function, LME.
Yeah, LM, right. That's the go-to for making linear models in R.
That's it. You tell it what your y variable is, what your x variable is, and where your data is. And then R does the OLS calculations for you.
So in R, that one little function does all the heavy lifting.
Yep. R gives you the estimated values for B0 and B1.
That's cool. So we've built our model. What do we do next?
Now we need to figure out what those numbers, B0, B1, actually mean for our real-world example. Like, we need to interpret them.
Okay, so if we're using that sales and advertising example, and let's say R gives us a B0, an intercept of, I don't know, negative 157.33, what does that even mean? Negative sales.
Well, technically, it'd be the estimated sales if you spent nothing on advertising.
Which doesn't really make sense for...
Often, no.
Yeah.
Like we were saying before, the intercept doesn't always have a clear real-world interpretation. It's just where the line crosses the axis. The slope is usually more useful. Let's say R gives us a B1, a slope of 2.77.
Okay, so what does that mean?
That means that for every extra, say, $100 you spend on advertising, we'd expect sales to increase by 2.77 units.
Oh, I see. So spending more on advertising should lead to more sales.
Based on this model, yes. And based on these coefficients, you can write out your model equation like this. Sales equals negative 157.33 plus 2.77 times advertising.
So now we have an equation we can actually use to predict things.
Right. But we need to make sure our model is actually reliable first. There are things we need to check.
Okay, so what needs to be checked?
Well, there are some assumptions built into this model, some things that need to be true for the results to be reliable. Like, the first one is linearity.
Linearity.
Yeah, we're assuming there's a straight line relationship between x and y. If it's curved or something else, our model won't work well.
So how do we check if it's actually linear?
First, you want to visualize the data, plot x against y, make a scatter plot, and just look at it. Do the points look like they're roughly in a line, or is there a curve?
Okay, plot the data first. What else?
The transcripts also say to plot the residuals.
Residuals, right. Those are the differences between the real sales and what the model predicted.
Exactly. And if it's linear, the residuals should be randomly scattered around 0. No patterns, like a curve or a funnel shape.
And the transcript said something about R squared, right? Something about you could have a high R squared even if it's not linear.
Yeah, they did. That's why visualizing the data is so important. You can actually have a line that seems to fit pretty well, but the underlying relationship isn't actually a straight line. R squared can be misleading.
Gotcha. And the transcript showed how to do these plots in R too, right?
Right. They use the plot function for that, and then to put the regression line on the plot, they use this other function, abline.
So if we see a curve in those residual plots, that's a bad sign.
Definitely. It probably means the relationship is more complicated than just a straight line.
Okay, so linearity is the first thing to check. What else is there?
The second one is constant variance, which is sometimes called homoscedasticity. It's a mouthful, I know. It just means the spread of the errors, so how much they vary, should be roughly the same across all the different values of x.
So like the scatter around the line should be consistent.
Yeah, exactly. You check that with the residuals plot too. See if the spread is consistent as you move along the plot.
And if it's not, like what if it gets wider in some places?
Well, that suggests the variance isn't constant. It can mess with your predictions. Like your model might be more confident in some areas than others.
Okay, I get it. So consistent spread is good. What's the third assumption?
The third one is independence of errors. That means the error for one data point shouldn't be connected to the error for another one. They should be independent, like flipping a coin.
Okay, so you don't want the model's mistakes to be related to each other.
Right. You can sometimes spot this in the residuals plot. If you see patterns like a bunch of positive residuals followed by a bunch of negative ones, that might be a problem.
Gotcha. Randomness is good. What's the last assumption?
The last one is normality of errors. It assumes that the errors, those residuals, follow a normal distribution. Like if you plotted them, you'd get that bell curve shape.
Ah, the bell curve. So how do you check for that?
There's this thing called a normal probability plot, or a QQ plot. And you can also just look at a histogram of the residuals. If they're normal, the points on the QQ plot should be close to a straight diagonal line, and the histogram should look like a bell curve.
Okay, QQ plots and histograms. Got it. Oh, and the transcripts also mentioned something about standardized residuals and outliers. What was that about?
Right, so standardized residuals, that's just a way of scaling the residuals.
Mm-hmm.
And if they're really big, like bigger than 3, that often suggests an outlier.
Outlier. That's like a data point that doesn't really fit with the others, right?
Exactly. And outliers can mess things up because they can pull the regression line towards them, making it less accurate for all the other data points.
They can really throw things off then.
They can.
So how do we even find outliers in the first place?
Well, we can use those standardized residuals if they're big, like we said. And there's another thing called Cook's distance.
Cook's distance.
Yeah, it measures how much the model would change if you took out a specific data point. If Cook's distance is big for a point, that point is probably an outlier.
I see. So we can use these tools to find points that might be skewing the results. And what do we do if we find one?
Well, you don't just automatically delete it. You have to figure out why it's an outlier.
Mm-hmm.
Is it a mistake in the data? Or is it just a genuinely unusual data point?
So first, figure out the why.
Right. If it's a mistake, fix it. If it's not, then you have to decide if your model is still appropriate. You might want to run the analysis with and without the outlier to see how much it changes things.
That makes sense. Don't just blindly remove outliers. Okay, what else did the transcripts talk about?
They talked about R squared and the correlation coefficient.
Okay, R squared. That's a measure of how well the model fits the data, right?
Yeah, it tells you the proportion of the variation in Y that's explained by X. like how much of the changes in sales are due to changes in advertising.
And it goes from 0 to 1.
Right. 1 means the model perfectly explains the variation in y, and 0 means it explains none of it.
So higher R squared is better, right?
Generally, yes. It means the model is doing a better job of capturing the relationship between the variables.
And what was that formula they gave for R squared? Something about sums of squares?
Yeah, it's either SSR over SST or 1 minus SSE over SST, where SSR is the sum of squares regression, SST is the total sum of squares, and SSE is the sum of squared errors.
That's a lot of sums of squares.
I know, but the good thing is R calculates it for you.
Oh, that's good. So we can just look it up in R. What about the correlation coefficient? What was that, like an R value?
Right, the correlation coefficient R. It measures how strong and in what direction the linear relationship is. It goes from -1 to +1. +1 is a perfect positive relationship. -1 is a perfect negative relationship. And 0 means no relationship.
And how is R related to R squared?
R is just the square root of R squared. The sign of R will be the same as the sign of the slope, B1.
Okay, so they're basically measuring the same thing.
Kinda, yeah. But there's a catch, a big one actually.
Yeah.
The transcripts stressed that a high R squared doesn't mean you have a good model.
Really? Why not?
Because you can have a high R squared even if the relationship isn't actually linear. That's why you have to check those assumptions we talked about, no matter how good R squared looks.
So R squared is helpful, but not the whole story.
Exactly. It just tells you how well the line fits, assuming a line is the right fit in the first place.
Right. Makes sense. Okay, so we've built the model, checked the assumptions, figured out R squared and all that. What can we actually do with it now?
Well, we can use it to predict things. The transcripts talked about the difference between prediction and estimation.
Right, prediction and estimation.
Estimation is using the model to figure out the average value of y for a given x. Prediction is using it to forecast a single new value of y for a specific x.
Okay, so estimation is for averages and prediction is for individual cases.
Exactly.
And the transcripts showed how to do a prediction manually using the equation.
Yeah, they plugged in a specific value for advertising spending into their equation and got a predicted sales number.
Simple enough. And then they talked about extrapolation. That's when you try to predict stuff outside of the data you use to build the model, right? And they said that can be dangerous. Why is that?
Because the relationship you saw in your data might not hold true outside of that range. Like, what if in your data, the highest advertising spending was, say, $60,000, and then you try to use the model to predict sales for $100,000 in spending? There's no guarantee the relationship stays the same.
Oh, I see. It's like your model doesn't know what happens outside of the data it's seen.
Right.
Okay, so no extrapolating too far. Got it. What was the last thing they covered?
Statistical inference.
Statistical inference. That sounds complicated.
It's really about using the results from our sample to draw conclusions about the bigger population.
Like, how do we know if what we found in our data is actually true for everyone, not just our specific data?
Exactly. That's what statistical inference helps us figure out.
Okay, so how do we do that?
The transcripts focused on hypothesis testing for the slope, B1. The idea is to see if there's a real relationship between x and y, or if the slope could just be 0, meaning no relationship.
So our hypothesis is that there's no relationship.
That's the null hypothesis, is what we're trying to disprove. The alternative hypothesis is that there is a relationship.
Okay, so how do we know which one is true?
We look at the p-value.
The p-value, right. That tells us the probability of seeing our results if there is actually no relationship.
Right. And if the p-value is small, usually less than 0.05, we reject the null hypothesis. We say there's evidence for a real relationship.
So a small p-value means there probably is a relationship.
Yeah, it's evidence against the idea of no relationship.
Okay, p-value, got it. And what were those confidence intervals they talked about?
Confidence intervals give you a range of plausible values for the true slope or intercept in the population. Like, we might be 95% confident that the true slope is between, say, 2 and 3.
Okay, so confidence intervals give us a range of possible values.
It's exactly.
Wow, we covered a lot today.
We did. We talked about the regression equation, how to build a model, how to check if it's reliable, how to use it to predict things, and even how to do some statistical inference.
That's a lot, but I think I'm starting to get it.
I think so too. And, the more you use it, the more it'll make sense.
I hope so. So now that we've learned all this, what can our listeners do with it? What should they be thinking about?
Well, I'd say think about what relationships in your own life or work you're curious about. What things might be connected? And remember those assumptions we talked about. Make sure to check those carefully.
That's a great point. Linear regression can be a powerful tool, but you got to use it responsibly.
Absolutely.
Well, I think that's about all the time we have for today. Thanks for joining us on this deep dive. And if you have any questions or comments, feel free to reach out to us. We'd love to hear from you.
Yes, definitely reach out. We love hearing about how you're using these ideas.
All right, until next time.
See you then.